Hey there, today we're going to talk about stoichiometry, which is like one of those very foundational things in chemistry, this odd word stoichiometry. But we'll get back to that. We'll talk about it in just a sec. So the idea is we want to be able to answer questions like the following. So let's consider this question. If I have 60 7/10 grams of methanol, how many grams of water will be produced if the reaction goes to completion? So our first question should be, what reaction? Because we need some type of chemical equation that we're talking about for stoichiometry. And you'll also find that we need it to be balanced. That's one of the reasons we have to learn about balancing chemical equations before we can talk about quantifying them through stoichiometry. Now, some people might find this question a little bit intimidating. I know I certainly did when I started in chemistry. So let's actually step out of chemistry for a second and into the kitchen. So you might have heard this joke before. What's the difference between cooking and chemistry? Well, in chemistry, you can't lick the spoon. But there's a lot of chemistry that happens in cooking, and in addition to that, the kitchen can provide us with some really good analogies for chemistry as well. And that's what we're going to do today. We're going to talk about crepes. Now, if you don't know what crepes are kind of like a skinny pancake. You can put all sorts of stuff in them. We like to put Nutella inside of them and then top them with like whipped cream. And they are a special occasion thing in our household. So here's the recipe for crepes. About 2 eggs, 1 cup of milk, 1 cup of flour, 2 tablespoons of some type of oil, and that should give you about 10 crepes. So let's consider the following question. If I have 10 eggs and lots of milk, flour, and oil, how many crepes can I make? So stop and think about that one for a second. Probably pretty quickly you come up with the idea that you can make 50 crepes. But just in case you're not quite there yet, let's actually go through the math. So based on my equation, if I have 10 eggs, and my recipe tells me that every 2 eggs can give me 10 crepes, assuming that I have enough of everything else, that's 10 times 10, which is 100, divided by 2, which is 50. So I can make 50 crepes. Another question I could ask, maybe I need to make 50 crepes. I'm going to have company over. We're going to have lots of crepes for my daughter's birthday. If I want to make that many crepes, how many cups of milk do I need to make sure I have? How many cups of milk am I going to need? And again, you probably in your head come up with the idea that you do the math in your head really quickly. But I'm going to go ahead and do it here just for people like me who can't do math very well in their head. If I want to make 50 crepes, and every 10 crepes requires 1 cup of milk, I can see from this then that I'm going to need 5 cups of milk. And when we look at this seems kind of simple. I have a recipe, and from the recipe I can take a certain amount of ingredient and figure out how much of the thing I can make, or I can take a certain amount of ingredient and figure out how much of another ingredient I need. So the truth is, this question, this problem that we're looking at, is no different. We have something and we want to know something else. We have a thing 1, we're looking for a thing 2. Or if we want to think about it in terms of crepes or a crepe recipe, this here, this 60.7 grams of methanol, this is like the number of eggs. This is how many eggs I have. I have a recipe down here, that's my chemical equation, that helps me understand then how many crepes I can make. So it's an eggs crepe problem. Now, what we're talking about here is called stoichiometry. Now, stoichiometry, you don't need to know the definition, but just since it is what we're doing, it's a method, it's a tool, and it's a way to describe the quantitative relationship between substances as they participate in a chemical reaction. So quantitative is just really kind of a fancy way of saying like the numerical or the number relationship. So it's a way that we look at the number relationship between substances as they participate in a chemical reaction, in the same way that we were just looking at the number relationship between ingredients in a recipe. And our recipe in this case, though, is going to be a balanced chemical equation. And the reason that it's so important that it be balanced is those coefficients are going to, ignore my children, they're playing Minecraft. Coefficients of the balanced chemical equation help us create the conversion factors between the substances. Because in the same way, when you think about crepes, there's no relationship between eggs and milk outside of that recipe. I can't ask you how many cups of milk are there in an egg. That doesn't make any sense. But I can ask you, how many cups of milk do I need if I'm going to use 10 eggs? I can ask you that because I have a recipe. In the same way, there is no relationship between the grams of water and the grams of methanol outside of a balanced chemical equation. In the chemical equation, the coefficients, those numbers in front that we've been using for balancing, they're what help us understand that quantitative, that mathematical relationship. So in the same way that we could tell that every 2 eggs could produce 10 crepes, here we can see that 2 molecules of methanol can produce 4 molecules of water. However, as you guys know, we aren't very likely to be able to measure in molecules. They're way, way, way too tiny. So instead, our molar ratios tend to be in moles. So 2 moles of methanol can create 4 moles. We abbreviate moles MOL, which I think is funny. Like, it saved me so much time. Ha ha ha. Can generate 4 moles of water. And I can write this just like any conversion factor. I can write it however I need it. And that's going to help me because it'll help me figure out when I'm multiplying and when I'm dividing. So let's go ahead and try it. Let's look at this problem. If I have 60.7 grams of methanol, how many grams of water will be produced if the reaction goes to completion? So what is this really asking me? It's asking me to take, there's my reaction, mass of methanol, so grams of methanol, that's a measurable quantity, and predict mass of water from the reaction. But I don't have a conversion between grams of methanol and grams of water, do I? Again, I can't say how much water is there in methanol, how much methanol is there in water. That doesn't make sense. What I do have instead is the molar ratio. I have the molar ratio between them. So what I need to do instead is get into my molar quantity. I need to get into moles of methanol. I need to take the mass and figure out, well, how many particles of methanol is that? And of course, we count particles in moles. And the reason that I need to do that is that's the relationship that I have. I know that every 2 moles of methanol can generate 4 moles of water. So from there, I can get into moles of water. I can say, okay, well, if I had this many, this is, I had so many, 60 grams, and that turned out to be this many particles, and that'll make this many particles of water, and then I can get back into a measurable quantity, because of course I don't have a molimeter in the lab, but I do have a balance, so I do want to get back into the mass of water. So how do we do that? We're going to start with what we were given, that eggs information. We were given that we had 60.7 grams of methanol. And you'll notice that not only do I include the units, I also include the chemical that I'm talking about. And that's because halfway through our calculation, we're going to change what chemical we're talking about. We're going to go from talking about methanol to talking about water in the same way that in our simple math, we went from talking about crepes to talking about eggs to talking about crepes. So 60.7 grams of methanol, and I want to get 2 moles of methanol. How do I do that? I have to do it in a way that cancels out the grams. So do we know something that measures grams per mole? Of course we do. We can use the molar mass of methanol to go from grams of methanol to moles of methanol. Now, hopefully you feel like you have a good understanding of that calculation. And if you don't, you might want to rewatch those videos. But I have already calculated the molar mass of methanol to be 32.05 grams per every 1 mole. And I'm doing that by taking the molar mass of carbon, hydrogen, and oxygen in the appropriate numbers for the chemical formula and totaling up those. And I got 32.05. Now that I've done that, I'm not going to stop and do my math. But if I did, I would have answered the question, how many moles of methanol are in 60.7 grams? But that's not my ultimate goal, so I want to keep going. Now, I want to get into moles of water. So how do I do that? How do I make this step? This is where my molar ratios come in, the molar ratios from the balanced chemical equations. So I want to cancel out moles of methanol. So it needs to be in the denominator. And I want to get in to moles of water, right? So I look to my chemical equation for that, and I look at my coefficients, and I see that I have 2 moles of methanol generate 4, numbers coming from there, moles of water. Now, if I stopped and did my math right now, what I would have calculated is how many moles of water are generated. But again, that's actually not very valuable, very useful, because I don't have something that measures directly in moles. I have something that indirectly measures in moles, and that is my balance. So my last step here would be to get into a measurable quantity, to the mass of water. And I'm going to do that by using the molar mass of water to get back into grams. So I want moles to be on the bottom and grams of water to be on the top. So the molar mass of water is 18.02 grams per 1 mole. And you might look back and see that things cancel out properly. That's a good indication that you've set up your equation correctly, right? And that you are, in fact, in the units, not only the units, but also the chemical that we were looking for. So then I go to do my math. I am going to go ahead and do the making sure it cancel out. This is good. Moles of water. So I know that chemical cancels out too. And then I can see, even before I put it in my calculator, that I'm taking 60 times 4 times about 20, and then I'm dividing it by 30 and about 2. So I get some ideas on like what kind of number do I expect. I don't expect it to be huge. I don't expect it to be tiny. So when I put it into my calculator, what I end up getting is 68.2567 grams. But of course, I do want to consider sig figs. And this one here is my weakest link. It has the least number. My molar ratios are exact numbers here. So I'm not going to use them to determine my significance. So I have 3 sig figs. So my final answer, which I'm going to sneak down here, is going to be 68.3 grams of water. So in the same way that we can figure out if I have 10 eggs, I can produce 50 crepes from the recipe. We just figured out that if you have 60.7 grams of methanol, you can produce and collect 68.3 grams of water from this chemical equation. So another way to look at it that might help, just this is an image I found that I kind of like, is this is that measurable world. This is where I can measure. I can measure mass, so mass of reactant, mass of product, mass of, or we could be mass of reactant 1 to mass of reactant 2. And then but I have to switch down into the atomic sized world. I have to switch there and then go over before I can come back. I kind of like that. You'll notice that a lot of stoichiometry problems follow this pattern. We have mass of thing 1 or mass 1, and then we need to convert to moles of that same thing. How many moles is that? Moles of thing 1. Then we convert to moles of thing 2. This is where we change what we're talking about. We went from talking about eggs to talking about milk or something like that. And then finally back into some type of measurable. For right now, that's going to be mass. Mass of thing 2. So mass to moles to moles to mass. Mass to moles to moles to mass. That's the pattern that most of our stoichiometry problems will take. So here's another practice problem that you guys could do. What is the minimum mass of carbon necessary to react completely with 24.6 grams of boron oxide? And I actually don't have enough time left in my video to walk through it, but I can tell you that the correct answer to this is 14.9 grams. So that can show you if you're doing it right. And if you're not, send me an email or a message and we can walk through it together. Good luck, you guys. You're going to love stoichiometry. Everybody does.